Good afternoon, everyone. Welcome to the Autonomous Systems and Robotic Vision session of IMVC. My name is Eitan Kosman, and I have the pleasure of chairing this session today. Today we have an exciting lineup of talks that delve into various aspects of autonomous systems and robotic vision, with 7 talks scheduled, each lasting 10 minutes. Before we begin, I'd like to remind our presenters to adhere to the time limits so that we ensure that we are on time. And now let's proceed without delay to our first presentation. Our first speaker is Raphael Mamane from Nexar, a researcher specializing in autonomous mapping, and he is a part of the AI Automotive Group, leveraging crowdsourced vision data sets to create high-definition roadmaps for smart driving platforms. He holds an MSc from the Hebrew University of Jerusalem, and today he will present on Scalable HD-map creation from crowdsourced vision. So let's welcome Raphael.
Hi, everyone. Good afternoon. So today I'm going to speak to you about how we at Nexar are creating scalable HD maps from crowdsourced vision. So who are we at Nexar? We're actually one of the leading AI dashcam brands in the United States. We have over 500,000 active users daily using our dashcams. And with all those users all around the world, and especially all around the United States, we're able to have a network of eyes on the road in the United States, constantly mapping out those roads. So we visit around 94% of US roads at least once a month. We also have AI and ML algorithms running on the edge on our dashcams, and we are actually collecting over 40 million detections every day, and we're also anonymously collecting data from our users, over 3 billion miles of video a year. So today I wanted to speak a bit about HD maps. So the future of autonomous vehicles and autonomous driving is going to rely on HD maps. So HD maps are very, very accurate and sub-meter accurate maps of our roads, road geometries, road assets, other kinds of for road furniture making up our road. And today, the way HD maps are made is extremely unscalable. So HD maps, the way they're made today, requires a large fleet of really expensive vehicles, expensive equipment, requires LiDAR equipment, large teams of annotators, manually annotating and making and building out these HD maps. And by the time they're done, the road has already changed. And there now needs to be a new map made, and it needs to be frequently updated, and this is just not a scalable solution. So at Nexar and on our research team, we're thinking, can we create these HD maps using our consumer dashcams? So our consumer dashcams are not this expensive, complicated, sophisticated cameras or equipment. They're very good, but they are monocular. We don't have any kind of depth information from our cameras. We have a very large range of cameras. They're not usually calibrated. The quality is we have high resolution, but they are still consumer level. And most of our cameras in our range don't have very high precise localization capabilities. We don't have any 360-degree cameras. So taking all this into consideration, can we make an HD map from these simple images? So from these consumer dashcams. So we start off by collecting frames, and we choose the best frames based on detections we make on the edge. So we have object detectors and other algorithms running on the edge on our cameras, and we're able to then pick and efficiently pick out the kind of best images we want based on maximizing information, ensuring good lighting, and we're able to kind of select a nice selection of frames from a region that we're interested in mapping. we then upload them efficiently. We anonymize, obviously, all the important elements in the image, and then we're able to feed it into a structure from motion pipeline. We're able to, we're using state-of-the-art feature matching and feature extractors such as aliked and light glue, and then using ColMap, we retrieve the poses and create like a reconstruction of the area we're interested in. And at the end of this process, we're able to generate a highly localized, dense point cloud of the scene we're interested in reconstructing. You can see here an example of a point cloud in Japan for a region we reconstructed. So now we have this point cloud. What we need to do now is infuse this point cloud with the semantics. So, for example, for traffic sign detection, for traffic signs, we're going to run a traffic sign detector, and that allows us to then go back into the point cloud and isolate out the elements and kind of isolate out each traffic sign separately and independently. For the road surface, we'll run a semantic segmentation, and we're able to then kind of segment out the road surface and understand which parts of our point cloud belong to the road surface. But that's not enough. We kind of want to know the road geometries, the different elements on that road surface. So in order to do that, we then fit a plane to that extracted road surface, fitting that plane using Ransack. And then now that we have a plane, we can take the pixels from the road surface that were semantically segmented, and we're able to then transform them and you do a homography in order to create what we call what's known as a bird's eye view of that road. So that bird's eye view kind of gives a perspective of what it's like when looking from above down at the road. But we've done that for one image, but our reconstruction is composed of many images. So what we do now is we then stitch these all together from the many different images that were fed into the reconstruction. So, thanks to the reconstruction, we have the poses of all of our images, and we're able to then create this very, very high quality HD view of our road surface. Very, very, the pixel resolution is actually very, very high, higher than if you were to take a satellite image, for example. And now that we have this high localized view of the road from the bird's eye, we can then run a semantic kind of extraction on this view of the road. So lane detection, instance segmentation in order to get the lanes and to get the different road markings on the road. And this then all comes together we can do this for multiple different regions, and this can all come together into a kind of unified HD map of the road, different road elements viewed on the road. So we can see here within the point cloud the different road markings, lane markings, and on the map the different road markings, lane markings kind of coming together in a unified manner. And we're able to scale this out more and more, and we really think that compared to like LiDAR and the way things are done today with very expensive fleets and very expensive non-scalable things, we really think this is like a scalable solution going forward for HD maps, leveraging a network of crowdsourced vision in order to kind of collect, and collect the data and create these kind of high fidelity and highly accurate views of the road, and also update in real time based on changes or any kind of events on the road, generate new HD maps for certain regions, and create kind of this unified HD map of the world. So I'll just want to leave you with a view of our system. So we have kind of the visual evidence for many of the different elements we have, and we have all the different road markings, and we can also go in and see our point cloud, how everything just comes together, multiple point clouds seamlessly kind of merge together. We have all the different elements and road elements, and we're able to really kind of segment out different signs very precisely. These are things that, with a standard definition map, we wouldn't be able to do, kind of isolate each element separately and view kind of everything seamlessly coming together through this really nice visualization, and this is how everything really comes together really nicely. So I wanted to give a special thanks to Shmulik, Robert, and Ilan for working on this together, and I would like to thank everyone else here Thank you very much.